Hi, welcome back. So this is where we stopped yesterday, where we were talking about the self-attention block within the transformer architecture, and we saw that the entire self-attention can be done in parallel for all the capital T tokens, and it all happens through these matrix multiplications, right? So in effect, what is happening is the following, right? So this is what is known as a scaled dot product self-attention, and this is called one head, and soon we will see multiple such heads, but we will get there when we get there. But for now, just remember this is called scaled dot product based self-attention. So what exactly is happening here? So this purple box here, right, this is the scale dot product unit, right? So this is what is lying inside this purple block here. And now what is the input to the box? Let's see. So you get the key, query and the value matrices. How are these constructed? Originally, remember, at the input all you had were these h1 to ht, right? So you had these word representations for the t words, and we were calling them as h1, h2 and so on, right? Now from the h1, h2, what happens? You pass them through the linear projection, right, through the WQ, WK and WV matrices to get the QK and V matrices, right? So this is just multiplying WQ by these vectors, and you just stack up these vectors into a matrix so that you can just do WQ multiplied by that H matrix, right? Let's just call it H. Then you get the Q matrix. Similarly, WK multiplied by this gives you the K matrix, and WV multiplied by this gives you the V matrix, right? All of this happening in parallel as three matrix operations. Then you get the QKV, and then this is what happens inside the self-attention head. And at the output, what do you get? You get Z1, you get Z1, Z2, all the way up to ZT, right? So this is what we had seen when we ended the last lecture. Now this is called one head. So what do I mean by a head here? So this is one such unit which takes the inputs h1 to h2 and gives you the elements z1 to z2, right, or the refined representations z1 to zt, which also take care of the contextual information because they depend on the key, they depend on the value, and they depend on the query, right? So they take care of the contextual information. Now you could have one more such block, right? So you could have the same block repeated. So let me just call this z11, z21 and z1t. Right, so this is the output of the first attention head. Similarly, you could have the same block repeated where you have another set of parameters, right? So let me just call these W1, right? These are the first set of 8 matrices you have. Similarly, you could have another repeated block, right? And let me just show it on the next slide. We just repeat these two blocks, right? And now you have head 1, head 2, and head 1 is giving you representations Z1, and this is giving you representations Z2. Now, there are several questions here, right? Why would you have two heads? And then if you are getting these two representations, which one do you consider, right? So we'll answer those two questions. So but first, let us motivate, right? Why would you need multiple heads? And we have already seen this in a different context before, right? So we want to motivate multiple heads in attention, right? So one head is one scale dot product unit, which gives you Z1 to ZT, right? The representation Z1 to ZT, and I'm making a case for many such heads. So why am I doing this, right? So we have already seen this in the context of convolutional neural networks, right? So where we had multiple filters, right? So these are three different filters operating on the same image, right? And each filter essentially does the same thing. It has parameters, say W1, W2, W3. It just goes over the image and gives you an output feature map, right? And the reason we wanted to have multiple filters is that we were hoping that each filter may capture a different characteristic from the image, right? Some may detect edges, some may detect blurs, and so on, right? So that's why you had multiple filters, right? And more the filters, the more abstract representations you could compute, right? The same argument holds here. If you have one self-attention, then it will capture, it will learn one way of capturing the contextual information, right? But there might be more than one way of capturing this contextual information, right? So you might also want to have a situation where it focuses on animal with a very high attention, and you might also want it to focus on some verb with a very high attention, right? And both of these might be important because one is indicating that it is a pronoun for animal, and the other might be indicating that it is the object of this verb, right? And so in both of these you might want to capture. So one head could learn to give more attention to animal, the other head could learn to give more attention to this verb, right? So just as you had multiple filters to capture multiple characteristics from the image, you could have these multiple attention heads, right? And let's just look at it a bit more carefully, right? So here's an example. So the animal didn't cross the street because it was too tired, right? And I have the same copy of the sentence here, and now I'm trying to learn a contextual representation for it, and now I want to focus more on was, right? Because I want to know was, what is the subject of it, right? So it is the subject here, so I want to know that, so I want to capture that information by paying more attention to was, right? But I also earlier made a case. So what does that mean? If I'm learning the alphas, right? So if I'm learning, say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10th word. So if I'm learning alpha 10, then this is alpha 10 1, alpha 10 2, right? And this is alpha 10 11, right? So this is the attention that should be paid on the 11th word when you're computing a refined representation for the 10th word, right? And I want this to be high, right? But I had also earlier made the case that I want the attention on animal to be high because animal is the, it is referring, animal is the word for which it is the pronoun in this case, right? So that means if I were to compute again the weights, alpha 10 and so on, then I want this to be high. So I also have a case for this to be high, I also have a case for this to be high. So one way of dealing with this would be have two separate attention heads, right, and compute two alphas, one from one block of self attention, another from the other block of self attention, and this block could learn to give more importance to this alpha, and the other block could learn to give more importance to this alpha, right? Now of course this is slightly make believe, right? We understand that because we have already visited this in the case of recurrent neural networks, that there is no signal, right? We are not telling the model that hey, you need to pay more attention to was, or hey, you need to pay more attention to animal. We just hope that when we are looking at the final loss function, and if it indeed is beneficial to focus more on was, right, that means have a higher weight for alpha, which in turn will contribute accordingly when we try to compute the refined representation for say the 10th word, right, and that effectively reduces the loss, so it would then learn to have a higher weight for was, right? Similarly, if it helps, so this is Z 110. Similarly, if you had Z coming out from the other attention head, and this will also participate in the fuel computation and then participate in the loss. So if it helps that now this set of alphas should be such that it should focus more on the word animal, and if the loss dictates that, then the machine would learn that, or the model would learn that, right? So that we are not giving it an explicit signal, we are just hoping that by trying to minimize the loss, it has more freedom now. In some cases it can learn to put a high alpha here, in some cases it can learn to put a high alpha here, right? So you are making a better design choice by allowing it more choices, right, or allowing it more parameters in terms of the W's, the projection matrices, which in turn result in different alphas, right? So just making it a more flexible model which has more choices or more options to how to adjust the alpha in different cases. So it might choose to have alpha was high for one case, alpha animal high in the other case, and then do something different in the third head and so on, right? So that's the motivation for having multiple heads. I just already explained this, I'll just skip over this. The same thing, whatever I explained, that in one case it would want to focus on was, the other case it might want to focus on animal, and this is actually from a actual trained transformer, right? So we looked at the attention weights, there were two heads, and we looked at what the attention weights were, and we found that in one case it is giving higher, in one of the heads it is giving higher attention to animal, and the other head it is giving higher attention to was, right? So it does learn to do such things, right? So this is what a two-headed attention would look like. You would have the query, you have the query, key and value vectors, right, which are coming from your projections. Sorry, this should have been, this is the H matrix, right, which is H1, H2 all the way up to HT, and you get out here is Q, K, V, right. So this is again the H matrix, and what you get out here is Q, K, V, right. So you just have these two copies. Now this, as I said, would release Z1, Z2 all the way up to ZT, and I'll just call it Z1, 1 and so on, and this would give you Z1, Z2 all the way up to ZT, and I'll call it Z2s, right? Now what do I do with this? I have two representations now computed for this word H1 to HT, right? So now what do I do with these two Zs? Simple, I just concatenate them. So that's all I'm going to do. So you concatenate it, so you get a larger representation, and then you pass it through a linear transformation, right? So we'll see that soon, and then what you get is the final output, right? So let's just look at this carefully, right? What is happening here? So again, let me just look at some. Okay, it's important that I get rid of this, right? So this is the H here, okay, and let's just focus on H1, right? Now H1, suppose H1 was a 5 and 2 dimensional vector, right? So now what I could do is I will choose W to be 512 cross 256. Okay, I'm just giving you some example. So that means the projection which comes out, right, my QKV would be 256 dimensional, right, because it's 5 and 2 multiplied by a 5 and 2 cross 256 matrix, right, or rather actually this would be yeah, so you get it, right? So I'll just project it down, so this will be 256 dimensional, right? So at the output again I'll get 256 dimensional Zs in both the cases. Now when they concatenate, I again get a 5 and 2 dimensional output, right? And this I could again pass it through whatever transformation I want, right? For example, I could choose a 5 and 2 cross 1024, I could choose a 5 and 2 cross 256, or I could choose a 5 and 2 cross 5 and 2, right? And depending on that, I will know what my output dimension would be. If I choose this, then my final Zs coming out of here would be 5 and 2 dimensional, right? So let's just understand it correctly. So this H1 gave me a 256 dimensional Z1. This, through this network or through this self attention, I got another 256 dimensional H1, and then I got 5 and 2 dimensional output here, which then again I pass it through a linear transformation, right? So it's because you're going to concatenate, it makes sense that the output of each of these is small, right? Because if each of these is 5 and 2 dimensional, then you concatenate, you will keep growing larger, right? And typically you use 8 heads. So now if each of this is 5 and 2 dimensional, and then you concatenate them, then you'll get a 4096 dimensional output here, which is too large, right? Because it increases the size of the parameters, that will go through a linear transformation and so on, right? So typically what you do is, if you want 5 and 2 dimensional size here, right, then you make sure that each of your 8 heads gives you a 64 dimensional output. So when you concatenate them, you get a 5 and 2 dimensional output. So you start with the 5 and 2 dimensional output, you adjust these dimensions such that you get a 64 dimensional output at each of these heads. You have 8 such heads, so when you concatenate them, you'll again get a 5 and 2 dimensional output. Then you do an appropriate linear transformation. You could choose this one so that your final Zs are also 5 and 2 dimensional, right? So that's what you could do, right? So this is what a 2-headed attention would look like, and I've already told you how to extend it to multi-heads. You will just have the same block repeated as many times as you want, and then finally you would just adjust all these transformations, right? So as I said, I could let's just look at it again. If my H's are 5 and 2 dimensional, these are H's, then I pass them through, I multiply them by a 64 cross 5 and 2 matrix. So I get 64 dimensional outputs here, 64 dimensional outputs here. Same happens in all the 8 heads. So when I concatenate them, I get a 5 and 2 dimensional output, right? So whatever I started with, I get the same. So I can just adjust the parameters accordingly, and then I do a linear transformation to get my final Z1 to ZT, right? So remember, this concatenation is happening per word, right? That means the Z1 representations coming out of each of these are getting concatenated here. Then the Z2 representations coming out of each of these are getting concatenated here, right? So it's per word. So the input is a set of words. You have capital T word embeddings, and the output at this layer or at every layer, right? Here, 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 at all these layers, the output is again capital T embeddings, right? So that you should remember that. Okay. So we are done. So we have the multi-headed attention. Okay, so we are back to the basic block that we had. So this is what we had. We had these inputs coming in here, right? And then now we have seen this self attention in detail, which could be a multi-headed self attention, and I give it inputs H1, H2, HT, and then through all the processing that happens inside, I get outputs. I think I was calling these as S1, S2, all the way up to ST, right? So once I have got this, now I need to understand what happens in the feed-forward neural network, right? So let's focus on that now, right? And this encoder is typically a stacked encoder, so you'll have 6 such blocks, right? That's why I'm calling this a basic building block. This is one layer, right? So you passed in H1 to HT, you got out Z1 to ZT. Now this Z1 to ZT becomes input to another such layer, and again you get a new set of representations out from your capital T representations out, right? This we have seen that the output of one layer acts as the input to the next layer, right? So all of this looks identical in all these blocks, and there could be 6, 8, 12 such blocks depending on the transformer architecture that you are looking at. Now let's see what happens in the feed forward network. So now you had so these are what the final output is of the feed forward network is Z. This intermediate output coming out of the self attention, I should have called it S, and this is the input H1, right? So now what exactly happens in the feed forward neural network? Right, nothing, it's quite simple. So remember that each of these guys here is a 5 and 2 dimensional representation or some d-dimensional representation. It is going to pass through a feed forward neural network and again give you a d-dimensional representation at the output, right? That's all that is happening here. So feed forward neural network is only acting as a projection layer here, right? So yeah, so this is the input S1, okay? There's some intermediate being computed, let me just call it say M, okay, right? And then you get Z1 at the output, right? So this could again be 5 and 2 dimensional input, 1024 dimensional projection, and then again 5 and 2 dimensional output. And of course there would be a non-linearity here. You could use any non-linearity that you want, right? And typically it is one of the ReLU based, either GeLU or one of those non-linearities. Okay. And the same set of parameters, right? So this here would have some parameters, right? So you'll have some W's here and then some another set of W's here, right? So let me just call them W feed forward network, and let me call this W1 because it's layer 1 and W2 layer 2, right? So the same set of parameters will be used everywhere, right? So each of these S1s or SIs will pass through the same transition and give you the corresponding ZI, right? So that's what I'm going to show with the animation, that the same network is essentially being used everywhere, right? So you get this same output everywhere, right? So this yeah, so you have the same network for each position, and you use this as the, this is the non-linearity that you are going to use, right? So nothing great happening within the feed-forward neural network. Whatever output the multi-headed attention gives, it just projects it and then gives you back a final output, right? So that's all we are done with the. Yeah. So that's all we are done with the encoder layer, right? So this is one layer of the encoder, and now I could stack many such layers, but each layer the internal working would remain the same. Just the output of the previous layer will be the input to this layer, right? So nothing else changes, right? So we are done with the encoder part of the transformer. So the encoder is composed of n such identical layers, and each layer is composed of these two sub layers. One is the multi-headed attention and the other is the feed-forward neural network. So the computation is parallelized in the horizontal direction, right? So what do I mean by that is that you, of course, so if you have these n layers, right, of course you cannot compute all the layers in parallel, right, because layer 2 will take the output of layer 1 as input, right? So unless you have done the layer 1 computation, you cannot do the layer 2 computation, right? So when I say it's parallelized, it's only within each layer, right? So for a given set of input samples, right, within that layer, all the self attentions, all the alphas, all the z's, they'll all get computed in parallel, right? Unless I mean, earlier when, again I'll just repeat this because this is important. In the case of an RNN, when you were given H1 to HT and you had to compute Z1 to ZT, right? You first had to compute Z1, then Z2, then ZT and so on, right? And here we saw that using this large matrix multiplications, we get Z1 to ZT in parallel, right? You don't have to wait for the previous time step for the next time step to be computed, right? So this parallelism you see in every layer, but of course across layers the computation is still sequential, right? Because you need the previous layer's output to do the next layer's computation. You have the input, then the layer 1 outputs get computed, then it feeds to layer 2 and so on till the end, and each of these T cross 5 and 2 outputs get computed in parallel, right? And now this final output of the encoder, right, which is the output from the last layer, we are going to denote it as E, right? So we'll refer to it as E1 to E capital T because there are T such tokens in the input, and for each token you get this final refined representation which is contextual as well as gone through several layers of abstraction or several deep layers, right?